bond energies and bond length. We've been talking about how bonds form and how we can represent them with Lewis theory. And we had talked earlier about enthalpy changes of reactions. We can also use individual bond energies to estimate enthalpy changes of reaction. Note that this is an estimate. Well, that's just not a good color. Orange? No. I really like the green. I don't know why. So bond energy can be defined as the energy needed to break 1 mole of the bond in the gas phase. You might say, well, how can you have a mole of bonds? Well, if each molecule is having 1 bond broken, it's a mole of molecules having 1 bond broken. That's what we mean by a mole of bonds. Bond energy is always positive. Positive energy, remember, means that you're putting energy into the system. You have to put energy into a molecule to get the bond to break. They're not going to break and release energy. Energy is required to break bonds. Now, some bonds are stronger than others. A stronger bond is going to take more energy to break. So if you think of maybe you took 2 pieces of wood and you glued them together, and one of them you just used white Elmer's glue. It's going to require some energy to break apart the 2 pieces of wood, but you could do it. And another one you used Gorilla Glue, right? It's going to take more energy. So it's a stronger bond, but they both require energy to break. Here's an example. We're taking hydrogen chloride and breaking it into the hydrogen atom and the chlorine atom, and the energy required is 431 kilojoules. That's for 1 mole of hydrogen chloride. Compounds that have stronger bonds tend to be more stable. They tend to be less reactive because it requires more energy to break their bonds. Well, of course, bond energy is going to vary depending on the particular molecule. And so we talk about an average bond energy. And so they'll look at, for example, a carbon-hydrogen bond in a bunch of different molecules and average that. Because most of the time, an average is good enough. So if we look at a hydrogen bond in this compound, which is CH4, methane, that bond takes 438 kilojoules to break 1 mole of bonds. If we put 3 fluorines on that carbon, it takes 446, so it's more energy. If we put 3 bromines, it's 402. If there's 3 chlorines here, it's 401. So the energy varies a little bit depending on the exact molecule that carbon-hydrogen bond is in. But they come up with an average of 414. And double and triple bonds are going to have higher bond energies because they're shorter and stronger. So we find these average bond energies in a table. This one's from your textbook. And there's also, I believe, a larger one in the appendix. Then there's books like the CRC up there on the shelf. It's got pages and pages of them. Or you can also Google it, right? Couldn't do that when I was in college. Let's just look at maybe this oxygen bond here. An oxygen-oxygen single bond, 142 kilojoules per mole. The double bond, 498 kilojoules per mole. It's stronger. So how do we estimate an enthalpy change using bond energies? Remember, this is an estimate. Well, we remember that bond breaking is endothermic, positive energy. You have to put energy in to break the bond. Bond forming is exothermic. When the bond forms, energy is released. That's not something that's necessarily intuitively obvious. Like it makes a bond and that's like releases energy? Yeah, it does. Why does the bond form? Because the molecule is more stable that way. It's at a lower energy. What happens to the energy it had before its energy got lowered? Well, it has to come out. The law of conservation of energy is super important because energy has to be accounted for. So to estimate an enthalpy of change for a reaction, we just add all the energies for the bonds that are being broken and formed. So you can state that mathematically this way. The enthalpy change for a reaction is the sum of the delta H's for the bonds that are broken, and that's going to be a positive number, plus the sum of delta H's for the bonds formed. All of those are going to be negative. So the signs are the trickiest part of doing problems like this. So here's an illustration of how we think about this. So say we're looking at the reaction between CH4 and Cl2. And it forms CH3Cl and HCl. So we look at this and we'll say, well, what has to be broken before these things can be formed? Well, we need to break one of these carbon-hydrogen bonds, and we need to break this chlorine-chlorine bond. So we'll figure out how much energy has to be put in to break those two bonds. And then we're forming a carbon-chlorine and a hydrogen-chlorine bond. And so that's going to be energy being released. And we add those together, and that gives us the estimated enthalpy of reaction. Any questions? Does that concept make sense? Does this look like some diagrams we had earlier? Yeah, same idea. We often say that energy is stored in chemical bonds, right? Why does gasoline power your car? Because there's energy stored in the chemical bonds. It's chemical potential energy. But breaking a chemical bond always requires energy. Things like gasoline or TNT, which are energy-rich compounds, undergo reactions in which weak bonds are broken and strong bonds are formed. It's the formation of the strong bond that releases the energy. So the forming of the bond releases energy. Let's do an example. A potential future fuel is methanol. Write a balanced equation for the combustion of gaseous methanol and use bond energies to calculate the enthalpy of combustion in kilojoules per mole. This will be fun at 7:20 in the morning. Well, combustion, here's our CH3OH. Combustion requires what? Oxygen. So we need O2. And what are the products? Water and CO2. Combustion of a compound containing carbon, hydrogen, and oxygen will always be water and CO2. So then we have to balance this. One carbon, 4 hydrogens. We've only got 2 over here, so we need 2 hydrogens there. 2 oxygens. There's 4 oxygens here. There's 3 over there. So that's going to be a problem. This is one of those fun ones. Well, let's try 2 over here. And that's going to bump this up to a 4. Because we need 8 hydrogens. 8 hydrogens and 8 hydrogens. And that's going to make this a 2. And see if this helps at all. Now we've got 2 oxygens and 2, so there's 4 over here. We've got 4, and 4 is 8. So we've got 8 oxygens over here, and we need 8 on the left side, 2 in the methanol, and then we can get 6 from oxygen. There we go. A little bit of a round and around, but not too bad. Got to have the balanced chemical equation. So doing a problem like this, we have to figure out what bonds are being broken and what bonds are being formed. There's 2 approaches to this. One is to say, well, I don't want to think about it too hard. I'd rather just break everything and then put everything back together. In a sense, that's safer because there's less chance of making a mistake. But it's a lot more numbers. So let's try to do it the more thinking way. We have to look and see what bonds are being broken over here. Well, we kind of have to look at how these things are put together. So the methanol is going to look like this. And oxygen's like this, double bond. So you really might want to actually do the full-out Lewis structures to make sure that you're not imagining things. Because if you just think about O2 and breaking it, you might assume that it's a single bond, but it's not, it's a double bond. And then over here, we have water and carbon dioxide. And let's just finish those out. And so we have to figure out how many of what kind of bonds are being broken and how many of what kind of bonds are being formed. In looking at this, it appears that there are very few bonds that are actually being retained. There's hydrogen-oxygen here, and there's hydrogen-oxygen over there. All of these carbon-hydrogen, carbon-oxygen single bond, those are all being broken. The oxygen-oxygen double bond is being broken. And all of these, except this one, are just being formed out of nothing. So since there's so much going on, we might want to just do everything. Question?
When I looked it up, it's CO2 forms from carbon monoxide, right? It's a two-step from carbon to carbon monoxide to carbon dioxide.
What we're basing this on is the fact that enthalpy is a state function. And so we are not actually commenting on how it actually occurs, which is nice because that opens a whole other can of worms. But you're probably correct that it makes carbon monoxide first. I don't know off the top of my head.
I just think you don't have to break that carbon oxygen bond.
This is a single and this is a double. And so, I mean, I'm sure there are people that can just rattle off exactly where the electrons are moving and which bonds are being formed and broken and how. But at this level, we can't even begin to think about that. But that's a good point. So since I see that there's a whole bunch of stuff going on, it might be easier to just look at all of the bonds. Sometimes you'll notice that, well, all of these are staying the same and there's just one being broken here. Then it might be easier to do one. So I'm going to pretend that I'm going to break all the bonds. I think of this as, being some Lego structures. And instead of trying to figure out, well, what part of it can I leave intact to make these things over here, I'm just going to say, let's take everything apart, individual blocks, and then let's put everything back together. The result is the same. So we've got what I'm going to do over here on the left. Well, that's fine. Is I'm going to list off the different kinds of bonds and how many there are. So we've got carbon-hydrogen bonds. We've got a carbon-oxygen single bond. We have oxygen-hydrogen single bond. And we have oxygen-oxygen double bond. Did I miss anything? Let's look at let's look at oxygen first. We have 3 of these molecules. So that means we have 3 double bonds that are being broken. So there's 3 of those. We have 2 of these molecules. In each molecule, there's 1 oxygen-hydrogen bond. So 2 are going to be broken. We have 2 carbon-oxygen single bonds. In each molecule, we have 3 carbon-hydrogen times 2, so 6. Did I do that right? No? Yes, okay. Because if you say no, you have to tell me why it's wrong. So over on the right side, I'm going to make a tally here. So I've got hydrogen-oxygen bonds, and I've got carbon-oxygen double bonds. That's all I've got. So in here, there's 2 in each molecule and 4 molecules. So 8 of those. And over here, I've got 2 of these bonds in each, 2 molecules, so 4 of those. Now that we've listed all this out, we can see that the only overlap is these 2 guys. And we're just going to stick with our plan and break everything and put everything back together. Now we need bond energies. Okay, so I'm going to write these on the board because I can't remember this long. Carbon-oxygen double is 736, except there's an asterisk. And down here, it's 799 in CO2, and that's what we've got. So that's 799. And then we're looking for, we had a carbon-oxygen single bond, it's 360. And we had carbon-hydrogen single bond, 414. We had hydrogen-oxygen single bond, 464. Did I miss anything? Oxygen-oxygen double bond. So that's right here, 498. Okay, so now we can go back to this. When I break bonds, is it positive or negative energy? It's positive. I have to put energy into the molecule. So all of these are going to be positive numbers. So carbon-hydrogen was 414, and that's times 6 because there's 6 of them. Carbon-oxygen, 360 times 2. Oxygen, hydrogen. Did I miss that one? I missed it. This is carbon, hydrogen. I'm lost. Hydrogen, oxygen, 464. 464, 2 of those. And oxygen, oxygen double bond, 498 times 2. I mean, it's kind of like running a fundraiser or something, and this is all the stuff I have to buy. I need 6 of these, and this is what they cost. And then over here, this is what I'm selling, and this is what I'm going to get out of it, and then I'm going to add it up and see what my net profit is. That's the basic idea. So the bonds being formed, these energies will be negative. So the oxygen-hydrogen is minus 464 when we make it, because making a bond has to be opposite in energy from breaking a bond. And there's 8 of them. And that carbon-oxygen double bond is 799. That's a big guy. And there's 4 of those. So then you pull out your calculator. So I'm going to add these up. Minus 464 times 8 plus negative 799 times 4. So over here, this is minus 6908. And the units on this are kilojoules per mole. And then I need to add all of these guys up. 414 times 6 plus 360 times 2 plus 464 times 2 plus 498 times 2. And I'll write this sideways, 5128 kilojoules per mole. So when I add those two together, 5128 plus negative 6908, the sum is minus 1780.
Why do you multiply 498 by 2?
Why do I multiply 498 by 2? That is an excellent question. Because I was trying to trick you. No, because I had 2 on the brain. Thank you. There's no good reason for that, just none whatsoever. That's supposed to be a 3. Thank you. So that changes. Not exactly everything, but it changes a lot of things. Get rid of that. So the 5128 needs another 498 on it. So 5626. Is that better? Okay. So 5626 and the negative 6908. So minus 1282. Now, you got to think about this for a minute. We want the enthalpy of combustion of methanol in kilojoules per mole, meaning kilojoules per mole of methanol. This is the amount for 2 moles of methanol, because we wrote a balanced chemical equation without using fractions, which is what we're kind of used to doing. But if we want per mole of methanol, this is the amount for 2 moles of methanol. So we need to divide that by 2. So it's minus 641 kilojoules per mole of methanol. And I think what probably would make this less confusing is let's take the per mole out of this part. Because when you think about it, what are we multiplying? What's 6? What's this 6? 6 moles of those bonds, right? So I think if we think of it in terms of that, it'll be a little clearer. That we're just calculating the energy for this reaction, and then we're going to divide by 2 moles of methanol so we get this final answer. Any questions? If you can step back and see the big picture, this is not a hard thing. If you get bogged down in the minutia, it's really confusing. So try to step back, see the big picture. That was a discussion of bond energies. We also need to talk about bond lengths. An average bond length is the average length of a bond between 2 particular atoms in a large number of compounds. Just like the energy of the carbon-hydrogen bond varied slightly from in the different compounds, the bond length will also vary a little bit. And since we're interested more in an overall idea, we're going to look at averages. Double bonds are shorter than singles, triples are shorter than doubles, and we can see that here. carbon single bond with carbon, 154. The double is 134, the triple is 120. And we also see that the bond strength, or the bond energy, increases. Longer bonds are usually weaker. There are some exceptions, because of course there have to be exceptions to everything. Here's a table of average bond lengths. It's of marginal interest at this point.